Hey everyone, my name is Bo. I'm here to talk today about bridges, why I think they will go away or fade away over time, and what I think about what's coming up next. Some background on myself. I'm a co-founder and technical lead at Polymer, where we're working on connecting everything through IBC. Previously, I worked on distributed systems, database systems at a number of startups. So the agenda today is we're going to try to apply operating system design to blockchain design. We're also going to talk about the concept of enshrined interoperability, user space versus kernel space trade-offs, IBC as an ecosystem-wide standard, and how virtual IBC scales adoption. So operating systems are split into user space and kernel space. In user space, we have the applications that you and I use every day. In kernel space, we abstract away the many different computer architectures that underlie these applications. It will be quite challenging for application developers to develop if they have to understand the computer architecture internals of every computer architecture that they're building on. So if we apply operating system design to blockchain design, we have in blockchain user space smart contracts or application-specific modules running in a virtual machine, in the Cosmos SDK as an app module perhaps. And in blockchain kernel space, we have settlement, consensus. Perhaps we have Comet BFT over ABCI, for example. Currently, bridges are built in user space as smart contracts. These smart contracts represent a tax on innovation that's growing and that's limiting future innovation and ideas. The issue with user space interoperability is that when we want to enter user space to execute interoperability code, we're coupling with the transaction format, custom RPC endpoints, account model of every specific chain. This means that we need a custom relayer for every single chain that we want to integrate. This also means that we're exposing the internal chain data structures of every chain to every other chain. For example, if we're connecting to Ethereum, we're exposing the Ethereum state trie to other chains in the IBC network. We need a way to verify proofs into the Ethereum state trie that something was committed. Additionally, inefficient execution means that bridges are forced to make compromises, whether it's by offloading the network management of network topology and routing information to off-chain agents, or if it's by adopting lower or less ideal security primitives. Overall, we get a cost of maintenance that equates to O of n, where n is a number of unique chain types in the network. How can we reduce the cost of maintenance from O of n to O of 1? Before we start, I want to define a term. Enshrined is a term commonly used in the Ethereum research community. In the context of rollups, it describes rollup logic that has its logic or its validation logic enshrined into the L1 or the protocol or the L1 client itself. This is different from a smart contract rollup where the rollup's validation logic lives in the smart contract. Let's perform a brief review of the interoperability model before we continue. In the interoperability model, we have the application layer, transport layer, and state layer. The design of bridges today generally do not respect the transport layer because they need to make compromises due to inefficient execution. Additionally, they adopt less secure security primitives as well. They rely on, as I said before, they rely on off-chain agents to manage the network topology and routing information to communicate between chains. Enshrining interoperability would migrate the logic from user space into kernel space. This means that we move the transport and state layers from user space into the kernel, where the kernel now manages encoding of the network topology, routing information, and verification logic of chains. There's a few benefits to this approach. For one, we get standardization. This means that we can have a complete implementation of all three layers of the interoperability model without compromises. This allows us to encode the network topology and routing information on-chain instead of off-chain. Encoding this information on-chain allows us to prove state across chains and allows each chain to have sovereign ownership of its view of the rest of the network. And between chains, you can establish a chain of trust where this view of the network is chained together. We also get an equivalent representation of chains at this transport layer. That means every chain looks the same as every other chain at the network level. This allows us to do things like standardize on a single relayer implementation. It also enables us to decouple execution. We can decouple IBC execution from chain execution, IBC state from chain state. Once decoupled, we no longer need to share the same data structures. So we no longer need to we can avoid exposing the internals of each chain to every other chain. We then have the ability to reuse relayer infrastructure and proof verification schemes. We don't need to write a custom relayer anymore for every single chain that we integrate. Overall, we get reduced integration overhead. There's now a minimal interface between the IBC side and the chain side. We can expand on the ideas before. If we standardize on a single relayer implementation, we can remove this relayer completely and replace it with a peer-to-peer network. With a peer-to-peer network, we now have a shared mempool across chains where we have IBC transactions are visible. We can then apply ideas from ANOMA, such as heterogeneous paxos, to allow for cross-chain atomic transactions across the IBC network. You can apply this idea by taking the intersection of the validator set of IBC chains on the network, connect them together, form a new chain, which they call a chimera chain. This is temporary. You can transfer ownership over a subset of the keys in the IBC state to this new chain and allow executing or atomic commitment over this in the chimera chain. Afterwards, the chimera chain returns ownership of these keys back to the original chain. The design of IBC is already hierarchical in nature and is topology specific. So it respects, and you have a very clear distinction of the subset of keys which you would need to grant ownership over in the chimera chain itself. Another fun idea is the ability to have a standard account model across chains at the interop level. This means that we would be able to use interchain gas tokens. A user will be able to issue a transaction cross-chain or across many chains using tokens that they have on the source chain. Overall, enshrined interoperability looks pretty good compared to bridges. But I want to talk about trade-offs. There's no free lunch in computing. Everything has trade-offs. What are we trading off? When we target user space for interoperability, which bridges are doing today, we're trading off for short-term distribution and simplicity. This is inherently a short-term optimization. When we target kernel space, we're trading off for functionality, safety, and future-proofing. This is inherently a long-term optimization. At Polymer Labs, we're building for the millions of developers that will enter the ecosystem in the next 10 to 20 years, not for the next 1 or 2. And to enable these developers to do their best work, chain developers must take control of the interoperability narrative and decide on what standard to enshrine into the chain client itself, to standardize on the interoperability interface for these developers and allow for innovations like the ones we shared before. So how do we decide on an interoperability standard to enshrine? What are the properties that we want? The first property that we would want is we want the standard to be open. It needs to be a standard that is a work of a collection of entities, teams, individuals, and not owned by a single specific entity. We need it to be neutral. There should be no value capture or value extraction at the protocol layer. We need it to be decentralized. It should be permissionless to join at all layers of the stack, and it should ideally maintain or lower the trust required, or lower the trust assumptions required by the system overall. IBC is the best choice given these requirements. However, there are some issues with IBC adoption or IBC integrations, as many of you may be aware. So let's take a look at what IBC looks like today. We have IBC Go, which is implemented as a Cosmos SDK module. Inherently, this lives in user space versus kernel space and inherits many of the issues that I outlined before. At Polymer, we've been exploring the idea of decoupling IBC app layer from the transport layer. After decoupling the app layer from the transport layer, we have the ability to move the transport and state layers of the interoperability model into the chain kernel. This means that we have an asynchronous binding between applications and the tau layer of IBC. We call this approach virtual IBC. It decouples IBC execution and state from chain execution and state. This decoupled approach scales adoption. We call something that implements virtual IBC an IBC outpost. A local IBC outpost can enshrine IBC logic over the virtual IBC interface, or VIBCI, into the chain itself. Also, once decoupled, IBC execution can also be remote to the chain. A remote IBC outpost can remotely enshrine IBC execution into the chain via the virtual IBC interface as well. This allows for permissionless integrations of IBC. An array of these IBC outposts forms an IBC network mesh, and this becomes the basis for future innovation. Targeting user space is an undifferentiated approach to interoperability. The more you simplify, the more you become similar to all other bridging protocols. IBC should take the approach of a kernel space approach and target innovation and differentiation and future-proofing and scale. We want to get to a system where the cost of maintenance of the entire system is constant, or O of 1, instead of being O of n. Bridges today are similar to many of the proprietary networking protocols that preceded TCP/IP standardization. In the 70s and 80s, there were a number of companies building their own proprietary networking protocols. This period was coined the protocol wars. At Polymer, we spent time evaluating the protocol wars, seeing how it progressed, and seeing why TCP/IP was adopted as a standard. We've hired many experts, industry veterans from companies like Arista and Cisco with decades of networking experience to help tackle this problem. The idea is that we want to, over this period, this next 10+ year period of the interop wars, which we're in now, we want to help establish IBC as a de facto industry standard. During this period, there will be many competing proprietary networking protocols or interop protocols that will be seen as standards. Even during the protocol wars in the 70s and 80s, many of these protocols up here were seen as de facto standards of their time. In the same vein, as IBC gains slow adoption over the long-term time horizon, we'll see proprietary systems, perhaps, which I won't name, be seen as industry standards as IBC gains adoption over them in the long-term time horizon. And as always, please join us in building the future of IBC. Thank you.